Assalamualaikum and a very good day to everyone. We are Group 7 and today we'll be presenting our topic titled HVAC, Humidity Dynamic Control in Wet and Dry Processing Areas. So this is the members of Group 7. Our group consists of 12 members and each of us will be presenting a part of this topic. To begin, I will explain the introduction to HVAC. HVAC stands for heating, ventilation, and air conditioning. It is a system that regulates temperature, humidity, and indoor air quality in a building. HVAC systems are widely used in industrial facilities, commercial buildings, residential homes, hospitals, schools, and other institutions. Its main function is to draw in fresh outdoor air, conditions in the air by heating or cooling, distribute the conditioned air evenly throughout the building. The type of HVAC system used depends on the climate, building design, purpose, and budget. Okay, so the first HVAC type is the ducted split system. The system has two separate components, which are the indoor heating unit and the outdoor cooling unit. The heating unit usually uses gas, while the cooling unit uses refrigerant, compressor, and coils. A single thermostat controls the entire system, making it simple and effective for residential buildings. Okay, the next system is hybrid split system. It looks similar to the standard split system, but it has one advantage. The heating unit can operate using either gas or electricity. Electric heating saves energy, while gas heating provides faster heating. This hybrid system helps reduce overall energy consumption and cost, especially in climates that are not extremely cold. Okay, the next system is package heating and cooling system that combines both heating and cooling into one single unit. This unit is usually installed on the roof, attic or ground level and is connected through a single wall opening. There are two variations which are package heat pump and package air conditioner with optional heating strips. There are a few advantages which are lower installation cost, easy maintenance and compact design. Okay, the last system for the ducted type is zone system that allows different rooms or areas to have individual temperature control. This can be achieved by installing multiple HVAC units and using airflow dampers inside ducts. The benefits include improved comfort and increased energy efficiency because the system only conditions areas that are actually in use. Okay, the another type of HVAC is ductless. Okay, the first one is duct-free mini split. The duct-free mini split system is a ductless HVAC option that consists of an outdoor compressor, multiple indoor units, and a thermostat for each zone. One outdoor unit can support up to 9 indoor units, and it can also provide flexible zoning and reduce energy consumption over time. However, it may not be effective in extremely cold climate for heating. Okay, the next system is the hydronic heating system that use water instead of air. Its components include a boiler, pipes, radiator, and sometimes heated floors. The boiler heats the water and the heat is distributed through pipes to different areas. The system is known for providing consistent, comfortable heating, especially in colder regions. Okay, the next system is the portable spot cooler. The portable spot cooler is a small, mobile cooling unit. It works by drawing in ambient air, cooling it through refrigerant coils, removing humidity, and releasing warm air outside through an exhaust hose. It is easy to install and ideal for temporary setups or specific works areas. Okay, this is the last system for ductless type, which is portable heat pump. The system provides both heating and cooling. It works like a spot cooler when cooling, but when heating, it uses a reversing valve to absorb heat from outside and transfer it indoors. It is convenient, flexible, and suitable for location needing a portable temperature control solution.
The main goal of humidity control in HVAC systems is to maintain stable humidity levels in both wet and dry processing areas. This helps prevent product defects, microbial growth, and processing efficiency. In wet areas, we usually keep humidity around 50 to 60% to avoid overdrying. In dry areas, we reduce humidity to around 30 to 40% to prevent moisture absorption or mold. The main components are the air conditioner, humidifier, sensors, and the control unit. These work together automatically to balance the humidity. Before operation, we check the filters and sensors and confirm the humidity settings. During operation, sensors detect the humidity and the system adjusts automatically. After use, filters and drain are cleaned and data is recorded for monitoring.
Next, I will be presenting about the advantages and also disadvantages of the HVAC system in the food industry. First, HVAC system help prevent microbial contamination. By controlling the temperature, humidity and also airflow, the system can reduce bacterial growth and keep the processing environment clean and safe. Second, HVAC system improve product quality and also shelf life. Stable temperature and humidity ensure that food does not spoil easily and maintain its freshness during processing and storage. Next, HVAC system help companies comply with food safety requirements such as HACCP, GMP and also halal standard. A controlled environment reduce the contamination risk and meet regulatory guidelines. Another advantage is improved worker safety and comfort. A well-ventilated, cool and also clean environment reduces the heat stress and creates better working conditions for the employees. Lastly, HVAC system offers better control of odor and fumes. It helps remove steams, strong smells and also chemical vapors, which help maintaining a pleasant and safe environment in the processing areas. However, HVAC system also have several disadvantages. The first one is high installation cost. Food grade HVAC requires advanced filter, ducting and also equipment, making it very expensive to set up. Second, HVAC systems are energy intensive. They need continuous power to maintain temperature and also humidity, which will lead to high electricity bills. Next, they also require frequent maintenance. Filter needs to be replaced to prevent it clog quickly due to food particles and also moisture. Besides, ducts also need to be cleaned and regular servicing is needed to prevent contamination. Another disadvantage is the risk of airborne cross-contamination. If the system is not properly designed or clean, it may spread dust or microbes from one area to another. Lastly, system breakdowns can affect production. A failure in HVAC can stop operations, which will cause food spoilage and lead to financial loss. In conclusion, the HVAC system plays a critical role in maintaining food safety, quality, and also worker comfort. However, it also comes with challenges such as cost, energy use, and also maintenance. A well-managed HVAC system is essential for ensuring efficient and safe food production. Now, I will pass to the next presenter.
Next is the case study. So this research paper is about temperature and humidity model for predictive control of smart buildings. So the purpose of this study is to address the identified gaps in current HVAC system modeling approaches, which provide a valuable tool for advanced control methods and also ensuring accuracy across diverse real-world scenarios. So the problems in existing HVAC humidity control mentioned in the paper is first limited HVAC operating modes. Models usually handle only cooling or heating, which not all HVAC operations. The second one is simplified or omitted humidity modeling, where humidity is often simplified or ignored, which reduce comfort and also efficiency predictions. The last one is challenges with radiator temperature predictions, where external water supply variations make radiator temperature predictions become unreliable. So the solutions is use of gray box modeling. They use parameter estimation techniques to improve model accuracy while reducing data requirements. It strikes a balance between the need for accurate predictions and also the practical constraints of data availability, making it a strong choice for HVAC system control. The next one is case study involving UK food manufacturing business company. So the background of the problem is they want to upgrade HVAC system, specifically the dehumidification process, into production areas. This is because the existing system created challenges conditions which the heating coils that were used to dehumidify the air often ice up, which led to high energy use. So the solution to overcome this problem is by designing a single air handling unit to supply to two areas. So the air HU supplies filtered dry air at a fixed temperature from a water chiller and two cooling coils through the external mounted ductwork to the two areas of the factory. Then the system is controlled and balanced using duct pressure sensors and also flow grids. The dampers will help to control which area the air goes to and how much air each area gets. Three-point valves were installed for the two cooling coils to maintain the air temperature due to LPG drying circuit built into the AHU. So the new system delivers correct humidity levels using less energy. So the conclusion is the single air handling unit supplying two food production areas with different temperature and humidity criteria delivers the required conditions more efficiently than the previous system. So built-in safety features, maintenance tools, audit support make the system more reliable and complete.
Simple math problem. Before we begin the calculations, these are the main formulas involved in the problems. We have the formulas for sensible heat load, air changes per hour, and the coefficient of performance. I will apply each of these formulas in the examples. For the first problem, the cold room has a volume of 2,400 cubic feet and the guideline requires 6 air changes per hour. For questions part 1a, find the required airflow CFM. The original formula is ACH equals CFM times 60 divided by the room volume. Since we already know the ACH and the volume, we rearrange the formula to solve for CFM. So, the new formula becomes ACH multiplied by the room volume then divided by 60. When I substitute the values, 6 times 2400 divided by 60, the result is 240 CFM. For questions part B, find the sensible cooling load. Here, we use the formula sensible heat load equal to 1.08 times CFM times delta T. We already calculated the CFM as 240 and the temperature drop is from 30 to 20, so delta T is 10. Then we multiply 1.08 times 240 times 10 and they give the sensible cooling load of 2592 BTU per hour. For the second problem, the room requires 4.5 kilowatt of cooling and the HVAC system has a COP of 3.2. Part A, electrical power required. The COP formula is cooling output divided by power input. To find the power input, I rearrange the formula so that power input equals to cooling output divided by COP. So, 4.5 divided by 3.2 gives 1.41 kilowatt. For part B, energy consumption for 1 hour. For part B, we want to find the energy consumption for 1 hour of operation. We already found in part A that the systems use 1.41 kilowatt of electrical power. Energy is calculated with a simple formula. Energy equals to power multiplied by time. Since the power is 1.41 kilowatt and the time is 1 hour, we'll multiply 1.41 kilowatt times 1 hour, and the final answer is 1.41 kilowatt per hour.
For the industrial point of view, I will focus on the efficiency of HVAC humidity dynamic control in food processing facilities. First, regarding productivity and yield, stable humidity, typically between 40 to 60% RH, is essential for maintaining product consistency. Proper humidity control reduces moisture fluctuation, prevents condensations, and lowers microbial growth risk. This directly decreases product defects and increases overall yield, especially in drying process, bakery operations, chocolate productions, and dairy handling. Next, the carbon footprint aspect. HVAC systems contribute significantly to energy consumption, around 40 to 60% of total usage in many food plants. Higher humidity loads require more compressor work, resulting in increased carbon dioxide emissions. Using energy-efficient technologies such as inverter compressor, desiccant humidifiers, and heat recovery systems can reduce energy use by 15 to 30%. For IR 4.0 integration, many industries now use a sensor for real-time temperature and humidity monitoring. AI control systems automatically adjust the HVAC load based on actual conditions, helping reduce energy wastage. Cloud-based platforms are used for data logging, remote monitoring, and regarding periodic maintenance. To maintain long-term efficiency, HVAC systems require routine servicing. This includes monthly filter cleaning, quarterly humidity sensor calibration, coil cleaning every 6 months, and annual performance audit to check airflow, energy usage, and potential system leaks. Finally, for the OPEX profile, electricity is the major operational cost for small to medium food industry in Malaysia. A single HVAC system typically costs around 1,200 to 3,000 per month depending on usage. Implementing energy efficient components and AI optimized controls can lower operating costs by 10 to 25%.
Assalamualaikum and salam sejahtera. My name is Sharifah Helena binti Said Faizal with the metric number A203612. So in this slide, I will present about does the process, which is HVAC system, can increase the carbon dioxide emission or carbon footprint problem? Yes, it does. HVAC system, which include technologies like air conditioner, heat pump, and windows unit, are widely used to control temperature and humidity in homes, office, and buildings. With millions of houses and buildings relying on HVAC technology every day, this system directly contributes to increased carbon dioxide emission. But why does this happen? It because HVAC system require a large amount of electricity to operate. A lot of energy is needed to power the cooling and heating process inside the system. In many countries, including ours, this electricity is generated by burning the fossil fuels. When fossil fuels are burned, they release carbon dioxide along with other greenhouse gases, and these gases trap heat in the atmosphere, making them one of the primary causes of global warming. As a result, the use of HVAC system contributes significantly to the carbon footprint and has negative impact on our planet. Despite this, HVAC system remains essential for comfort and safety. Because of this importance, it's crucial for us to find ways to reduce the carbon footprint produced by this system. Here are several simple actions we can take, which first, lowering the thermostat by just 1 or 2 degrees. This small adjustment will not affect the indoor comfort very much, but it can have a surprisingly big impact on reducing carbon emission. Even a single degree lower can lower significantly cut carbon dioxide output. Second, make sure the HVAC system receives a regular maintenance. Proper maintenance keeps the system running efficiently and ensure good air quality. If filters are clogged or components are dirty, airflow becomes restricted, forcing the system to work harder to reach the desired temperature. This leads to higher energy consumption and more carbon emission. Third, good insulation is essential when areas like the roof, floors,
walls, basement, and attics are properly insulated, the HVAC system doesn't need to work as hard to cool or heat the building. This reduces both energy use and environmental impact. Lastly, reducing heat loss through unsealed walls, windows, and doors is important. Air leaks not only create uncomfortable draft, but they also cause significant energy loss. By sealing this area, we can improve indoor comfort and reduce unnecessary energy waste. In conclusion, while HVAC systems are necessary in our daily life, they do contribute to carbon dioxide emission. However, through simple steps such as adjusting thermostat settings, maintaining the system, improving insulation, and sealing heat leaks, we can reduce the carbon footprint and help protect our planet. So that's all from me. Thank you.
Next, I will explain how we can reduce the depletion of thermolabile compounds through proper heating, ventilation, and air conditioning maintenance and operation. First, we look at the filter maintenance. Dirty air filters will restrict airflow, and then when the airflow is reduced, the HVAC system need to work harder. This will cause the internal components to heat up more than they should. So for thermolabile compounds, which are easily degraded by heat, this overheating increases the risk of degradation. So we need to change the filters every 1 to 3 months to keep the system running at the correct temperature and prevent unnecessary heat build-up. Next is ensuring proper airflow. We have to make sure that the indoor vents are not blocked and nothing is placed around the outdoor unit, because good airflow is essential for the HVAC system to remove the heat efficiently. If the airflow is restricted, heat will trap inside the system, and this will increase the temperature, which can accelerate the breakdown of thermolabile compounds. So maintaining clear airflow path is a simple but crucial step in this case. And another important strategy is by keeping the evaporator and condenser coils clean. When the coils are covered with dust or debris, their ability to transfer heat and humidity drops significantly. As a result, the HVAC system becomes less efficient and become overheat. Clean coils will ensure the better temperature and moisture control, which can help preserve thermolabile compounds during processing or storage. Okay, now is the strategies to increase product yield. The first technique is pulse electric fields, or PEF. PEF enhances extraction efficiency and increases yield without using heat. This is very important because it helps to maintain the stability of sensitive compound. PEF uses quick electric pulses to break cell walls, which helps to release the compounds more easily without causing much heat damage, and will increase the product yield. Next is ultrasonication. This method uses physical forces, specifically ultrasonic wave, to improve mass transfer and speed up extraction. The vibrations will help to break down the cell structures, allowing more compounds to be released efficiently. Ultrasonication is widely used because it increases extraction rates while still keeping temperatures relatively low. Finally, by maintaining a low and stable temperature. When temperature is kept under control, we can avoid overheating during processes like drying or extraction. This will reduce product loss and also preserve compound quality, which leads to a higher yield. A stable temperature environment will help to ensure that thermolabile compounds are not degraded. So overall, by controlling temperature and also using the non-thermal techniques, we can protect thermolabile compounds while also increasing the overall product yield.
I will explain how IR 4.0 technologies such as IoT sensors, artificial intelligence, and cloud data improve HVAC humidity control in food processing. Humidity control is very important because it prevents microbial growth, protects product textures, and maintains product shelf life. With IR 4.0, the HVAC system becomes smarter. IoT sensors collect real-time temperature, humidity, and airflow data. AI or HAI then analyzes this information and makes automatic decisions to keep humidity stable. Cloud analytics stores the data, studies trends, predicts humidity changes, and helps optimize the entire system. In short, the workflow goes from sensors to AI to cloud analytics and finally to Hvac actions that maintain control humidity conditions. This smart humidity control system works in four main steps. First, IoT sensors are installed in both wet and dry areas to continuously measure humidity, temperature, dew point, and airflow. They quickly detect any sudden change and send the information to the controller. Second, AI or HAI compares the real-time data with the target humidity levels. It uses intelligence algorithms to decide when to adjust the dehumidifier, fan speed, cooling, or reheating to avoid condensation. HAI makes these adjustments very quickly because it runs locally on the equipment. Third, cloud analytics analyzes long-term trends and predicts when humidity will increase during production. The cloud system also recommends the best humidity settings for product quality and energy efficiency and supports HACCP and GMP documentation. Finally, based on these AI decisions, the Hvac system automatically adjusts the humidifier capacity, air temperature, airflow, and damper positions to keep the environment stable. In wet processing areas, such as washing, cooking, and cleaning, humidity increases very quickly. The sensors detect this rise, and HAI responds immediately by increasing dehumidification and ventilation. Later, the cloud system analyzes the data to improve future control strategies. As a result, condensation on surfaces is reduced and microbial risks become lower. In dry processing areas such as powder handling, snacks, packaging, and storage, low and stable humidity is crucial. If humidity is not controlled, products can be sticky or lose their crispness. AI helps maintain a narrow humidity range by adjusting the humidifier and reheater, while cloud data links humidity levels to product defects. This results in better textures, longer shelf life, and fewer rejected products. Using IR 4.0 technologies in Hvac brings several benefits. It improves food safety by reducing condensation and microbial growth. It also enhances product quality because humidity is kept at the ideal level for each type of product. Cloud-based data logging makes it easier to meet HACCP and GMP requirements, and the system runs more efficiently with less downtime. However, there are also challenges. Firstly, installing sensors and cloud system can be costly. Second, a secure data connection is needed for continuous monitoring. Third, older HVAC units may be difficult to integrate with new technologies, and staff must be trained to understand the data and operate the system correctly.
Before you look at the maintenance schedule, it is important to understand why regular HVAC maintenance is necessary. In food processing areas, we must maintain strict control of temperature and humidity to prevent condensation, microbial contamination, and quality defects. A well-maintained HVAC system ensures stable environmental conditions, reduces energy usage, and prolongs the lifespan of the equipment. Therefore, a structured maintenance plan is divided into daily, monthly, quarterly, and annual activities, each serving a specific purpose in keeping the system reliable and safe for food operations. Daily checks focus on detecting early signs of malfunction by ensuring that the system runs properly, confirming correct thermostat settings, and monitoring temperature and relative humidity readings. These steps help prevent sudden fluctuations that may lead to condensation, microbial growth, or product quality defects. Monthly maintenance involves inspecting and replacing air filters, ensuring that air vents remain free from blockage, and listening for unusual system noises. These actions help maintain optimal airflow, prevent contamination, and identify mechanical issues before they escalate. Next, quarterly maintenance requires deeper technical servicing, including cleaning, cooling, and heating coils to improve heat transfer efficiency, calibrating temperature, relative humidity, and pressure sensors to ensure accurate environmental control, and clearing the condensate drain line to prevent water buildup and mold growth. Finally, annual maintenance includes comprehensive cleaning of both indoor and outdoor courts, checking refrigerant levels, and inspecting connection for potential leaks, as well as evaluating the blower, control, and ductwork for signs of wear or corrosion. These major servicing tasks help maintain system reliability, minimize energy consumption, and extend the overall lifespan of the HVAC unit. Overall, this structured maintenance schedule ensures consistent product safety, stable processing conditions, and efficient operation throughout the year.
Protocols of CIP as a part of HACCP. Firstly, we need to understand why CIP is linked to this. CIP is a cleaning system for equipment and surfaces where it supports HACCP by preventing biology, chemical, and physical hazards. Where the higher humidity areas, the higher condensation risks, then it can cause microbial growth. HVAC parts can also accumulate biofilm, where it can cause contamination risks. So, this shows that CIP can ensure food safety in a moisture-sensitive environments. Move on to the standard CIP protocol set. The first one is pre-rinse, where we remove the surface residue using water such as moisture film and dust. The second one is caustic wash. We remove fat, protein, and carbohydrates at 60 to 80 degrees Celsius, where it can dissolve biofilm, and oils intermediate rinse, where we flush caustic detergent and prepare equipment for sanitization. This is done to remove any remaining detergent before moving to the next cleaning step, which is acid rinse. Here, we will remove mineral deposits, scale, and water hardness residue that is left behind by caustic wash. The final one is final sanitization, which we can use by two methods, which is chemical sanitizers and also thermal. For chemical sanitizers, we can use peracetic acid, chlorine dioxide, and quartz. For thermal, the temperature is between 80 to 90 degrees Celsius hot water to sanitize the system before starting. Lastly, is we need to do the HACCP requirements, which is monitoring and verification. We need to monitor temperature, flow rate, chemical strength, cleaning time, automated CIP sensors, and IoT data logs. We also need to do the verification by using ATP bioluminescence test, microbe swab sampling, and HVAC condensate swab test.
Now, we will move on to OPEX profile, which means operating expenditure. Here, we will discuss about the operating costs associated with running and maintaining HVAC systems. There are four key components. The first one is the energy cost. These come from electricity usage by compressors, fans, pumps, and all the control systems in the HVAC setup. The second is the maintenance and repairs. This covers routine inspections, cleaning, part replacements, and fixing system faults. The third one is the consumable and supplies such as filters, refrigerants, and other materials necessary. And the last one is the labor cost, which includes salaries and training expenses for technicians and staff who handle the system. Next, let's look at what's new in the updated electricity tariff implemented by the TNB. Firstly, we have a new base tariff where the average rate is now set at 45.40 cents per kilowatt. Second, we have new tariff structure where the bills are broken down into 4 components, which is energy, capacity, network, and retail charge. For non-domestic users, classification is now by voltage level, which is low, medium, and high voltage categories. The third one, TNB, has introduced more dynamic automatic fuel adjustment, or we call it AFA. This means electricity prices can go up or down more frequently depending on fuel price changes. And finally, there is an expansion of the time of use system. Rates will be lower during off-peak hours and higher during peak hours. This slide shows the OPEX profile for a small and medium enterprise using medium voltage electricity under tariff C1 to C2. Here, the charges are separated into time of use tariff, which include peak and off-peak periods. During peak hours, the energy charge is 31.32 cents per kilowatt, while during off-peak it is slightly lower at 27.23 cents per kilowatt. The capacity charge remains the same for both periods at 30.19 cents per kilowatt, and the network charge is also fixed at 66.87 cents per kilowatt. On top of that, SME are required to pay a retail charge of 200 per month. For example, a typical SME consuming between 10,000 to 12,500 kilowatt per month, where the estimated electricity cost ranges from 3,000 to 3,978 per month, excluding AFA. Now, let's look at the OPEX profile for large industry under the high voltage tariff. It's just the same as the SME. The tariff will split into peak hour and off-peak hour. So for the energy charge are 44 and 52 cents for the peak hours and 40.43 cents per kilowatt for the off-peak hours. Capacity for both peak hours and off-peak hours is 21.76. Meanwhile, for the network is 23.06 cents per kilowatt. So for the retail charge, it's a fixed, which is 500 ringgit per month. For example, using a typical large industry consumption of 150,000 to 170,000 kilowatt per month, the estimated monthly electricity cost from 65,000 ringgit to 74,000 ringgit. This estimation does not include the AFA, which may increase or reduce the bill depending on the monthly fuel adjustment.